Yeah, so last Thursday we did a walkthrough on how peers connect to each other, as well as some of the essential data structures we use in the network code. And today, Marcelo will share with us how the routing works in network. It's very complicated, and I hope it's going to be interesting to everyone. So I just hand over to Marcelo.
Okay, thanks for the introduction, Bowen. So, well, let's give a high-level overview about how it works and speak about how we discussed last week. Right now, like last week, we discussed about how two peer connect to each other and that they keep edges between them whenever they either create or disconnect from each other. They create an edge that contains that information. On the network level for routing, what will be happening is that these edges will be propagated through the network. So every peer knows about the status of other peers in the network, and they will use this information to route messages to their relevant destination, trying to use shortest path, but at the same time trying to balance the the information the information through trying to balance the information through several channels. Okay, so let's see how this works. I will use the same. I will share my screen, the code. Give me a second, please. Okay, done. Hopefully you can see it. If the size of okay. Oh, if it isn't, let me know. Okay, so initially I want to discuss what is happening immediately when two peers are connecting to each other. They will start to exchange certain information, which is the status of their routing table. What is the relevant information about the routing table? Well, we will be seeing today most of the code here in routing.rs and some of the code here, peermanager.rs. That's where most of the logic is happening. In the routing table, there is one relevant data structure over here. In the routing table, we will keep the list of all edges inside some graph data structure, which is just a graph containing all edges. And this is the information that we will be exchanging with all the peers, all the edges. With the peer we just connected, we will share all the edges that are in our graph right now. This is done at the moment in a very naive way. We don't check whether the intersection of our edges is large or small. We just share all the edges right now, which is fine for graph with low number of nodes, with small number of nodes, but we will need to improve this as our network scales. Okay. So there is another important piece of information that we will keep, and it's this mapping between account IDs and this called announce account, which basically contains the peer ID of each account. What is happening here is that we will keep a mapping between each validator ID, which a validator ID is just an account ID, and its relevant ID on the network. Like at the network level, we are referring to each node with a peer ID, which is a unique key. And we will have this mapping between validators and peer IDs. This will be relevant to route information to particular validators while they are while they are active validators on some epochs, because we need to route like information such as transactions, information pieces to synchronize, etc. So these two, let me share the code. I think it's here. So here it's the part of the code. Oh, sorry. Let me just remove this. When we connect to each other, we automatically send this type of message, which is a sync message that contain all edges and contains all accounts known to us. Notice that let us we inspected the edge data structure in the previous session, how they are validated and how we make sure the information in that edge is correct. Let us inspect how announce account work. So it contains basically the peer ID and the no, it's not this. Sorry. Yeah, it's very weird not having account ID. Yeah, this is the announce account that contains the account ID of the validator, the peer ID of the validator, the epoch for which this validator is going to validate. This is relevant so that we we know when this announcement expires, and basically they expire after the epoch passed. And we have this signature, which is basically this peer signing the full information. This would be relevant only for peers that are not necessarily validating in the network, because other this is relevant to because everyone, basically all validators, I think all the peers can verify if a validator belongs to the epoch ID. This is necessarily to validate, and the signature is just to check that this validator actually controls this peer ID, or basically control this peer ID. The opposite way, sorry. Like this signature is is signed with the key of the validator, okay? Because we want to avoid that anyone can claim any account ID, okay? So yeah. So this information, well, let me just make a brief pause. Like in the other session, you can ask any question in the chat and I will try to address it. So feel free to do it. I will be monitoring it. So well, here when we receive all edges in account, we just go through this process of validating them, which basically is validating signatures and checking, in the case of accounts ID, that they actually belong to an epoch that is not in the past, that it's the current epoch or the next epoch. So we can, this is also required for us to be able to validate it. This information needs to be passed to the client actor to be able to be done, either the client or the view client actor, to be able to validate it, since the peer manager doesn't have enough context to do it. So
yeah, it is passed to the view client actor.
Yeah, because it doesn't need to modify anything. It's just checking. Okay. Well, this is the information that is exchanged between two peers when they connect to each other. But another process is going in the background, that whenever a new edge is added to the network, this edge is automatically broadcasted. This should probably be happening in peer manager, register peer. Very likely in the end, we broadcast, exactly. We broadcast this message, which is basically a routing table update, routing table sync, but it only contains a single edge. Okay, so this edge is broadcasted to the network to let other peers know that there is that this connection exists, and the same is happening with validators. There is a background process running. Not a background process running, but you can check here.
Yeah, I think it's called check send announce.
Check send announce account. Here it is. And in this function, if when we are validators, this function will trigger this event that basically will be broadcast the information that we will become validators in the next epoch. So this information is broadcasted way ahead of we becoming validators, so that everyone have this information in their routing tables before we are actually validators. Okay, this is probably the most relevant part about synchronizing information between peers. Let us discuss about how how we'll be routing messages. So with this information, whenever we receive any new edge to the network from the network, we add it to the routing table, which basically will add it to this graph. This is the raw. This graph will contain the raw information, all the edges, and will be used to process shortest path to all the nodes, since we want the message to travel the list through the list through the path with least number of edges. So let's see how the graph works. Basically, just a store for every edge is just a pair of peer IDs. From the point of view of the graph, it doesn't matter the signatures. We at this point, those should be verified already. So we have this adjacency matrix. I expect you're familiar with that. For every peer, we have the set of all peers which are connected to that peer. We also keep source, which is basically our peer ID. And then in the graph, we have this important function, which is calculate distance, which basically, for every peer in the network, it will give us the set of peers, the set of peers connected to us that belong to the shortest path from us to that peer. Okay, so for example, let's see if I have some example drawn here. I think there is some drawings in the test. So here, suppose in this test that S is connected to 0, 1, 2, and these are fully connected to 3, 4, 5, and these are fully connected to 7, 6, 7, 8. Then for the set, for the 8 set, we say that all these peers, 0, 1, and 2, belong to the shortest path to 8, because there is a path of length 3. So there is a path from S to number 8, to node 8, of length 3, and they're the same through 0 and through 1. So basically, we can send any message from S to 8 through any of those nodes. And we will, well, in this case, it's not like all our neighbors work, but it doesn't it doesn't need to be necessarily the case. For example, for node 2, the only peer that belongs to the shortest path is the node itself, of course, because any sending information through other nodes will make the path longer. Like if we send it through one, it doesn't make any sense, of course, if we want to send a direct message. So basically, this function is running BFS. This function is running BFS to compute for every peer what are the neighbors that we can select to send a message that uses the shortest path. And usually this is triggered on this. Sorry, let me now go back. In the peer manager, on the routine itself, there is a function that let us find. It's fetch rootback, not rootback. Sorry. Probably touch.
I think it's update, right? It's computing
find root. It's find root. Like yes. I wanted to find there is this function. Probably this one is better. Find root from peer ID, which when we call this function, it will find to what peer we should. It will find one active peer that we have right now that will be the one that will be sending the message, and this peer will at the same time route the message to the target. So in this case, this is the target, and the result will be the peer that we will immediately, that the next hop in the path. Okay, so basically there is some extra logic here, because what will happen is that when we receive new edges, we automatically will call update. This is not done on every update. We will try to make some batches, but to avoid the routing table to go out of sync, we don't wait more than 1 second to update the routing table, to update the shortest path to all other nodes. So basically, when we call this function, we can safely call peer forwarding. This will give us a list of routes to which we can send the message to, and then we will do something. We will do round robin to select what is the peer that we have selected the list to send message through it, to try to balance all the message we are sending. And this is some sort of round robin. It's adjusted since edges are coming and going. So we are just having like nonsense about how many messages we have sent through node. But this nonce, for example, when we add a new edge, we add it with the nonce of the lowest nonce about all connected peer we have right now. This is just to avoid like sending several messages through a newly created edge and saturating it. We don't want that at any moment. So, okay, this is the main idea about how we are selecting a peer to send to send message through the network. And well, these messages are very particular type of message. Let me show you how do they look like. These are rooted message body, but we don't want that. We want rooted message. Yeah, this is it. The rooted message contain the target. This is the target of the message. We will see shortly why there is peer ID or hash, but basically this is just an unknown about if we are routing to a peer ID or to a hash. Right now, let's assume it's just peer ID. So if it's peer ID, we are trying to send a message to this peer ID. This is the author. Well, it speaks for itself. We are the author of this rooted message will sign it. But if the message contains any invalid, like if this message is somehow invalid, which I don't think it can be in any other way than the signature, the one penalized is the previous, like if the signature is invalid, if I receive a message from a peer with an invalid signature, the one penalized is of course the previous hop in the path. But otherwise, this is not checked. The content of this body is not checked in any way. So when this message arrives to the target, if it contains some invalid information, the only one that should be penalized, if should be penalized at all, should be the author of the message. Okay. So let's see now what this hash is. So basically, we have this routing mechanism because there are certain type of message that arrive.
Marcelo, sorry to interrupt, but I think we've just covered a very important chunk of the network, and I want to see if people have questions regarding the how the routing works and how the graph is computed and maintained.
My question is how, because my understanding is that we keep the whole information about all graph or the edges, and how are you planning to actually scale that if we want to have higher number of nodes?
So for the moment, we have some background process, like I don't recall if it's actually implemented, but there is some garbage collection on top of our routing table to remove parts of the graph which are not relevant to us. And basically the part of the graph that are most relevant to us are those that are connected to validators itself, to peers that are validators. So we don't necessarily need to keep a full view of the network. We only need to keep a view of the network that led us to connect to validators, which are basically the most important nodes in the network. Probably we can do something similar maybe with archival nodes or something like that. But like the idea,
but basically what you are saying that if you need to connect to all validators, then you still need to store almost the full graph if you need the list of all validators.
Like we have discussed how many validators we might be expecting in the future, and it's on the order of hundreds, not thousands. And I think hundreds is already a high number. And even for 1,000, the current approach is fine. Probably the current approach will break with tens of thousands. it will be most noticeable, will start to be noticeable. So for current expected number of validators, that should not be a problem.
But what about the number of what about the number of nodes on the network? Is it expected to be much higher than the number of validators, or is it also going to be limited?
Like the point is that we don't need to keep full of all the nodes that are not validating. We only need to keep a subset which is enough to have direct routing to validators and fast routing. I mean that the distance to validators is small, is short.
Yeah, but to answer Piotr's question, yes, the number of nodes is expected to be much larger than the number of validators on the network.
Okay. So just for the record, the graph, like right now on mainnet, Bowen may correct me, or maybe Michael, there are like hundreds of nodes validating and not validating, and the diameter of this graph is 2. So routing message need only to traverse through only one extra hop. So yeah.
How do you ensure that the diameter of this graph is 2?
Like we don't have anything in particular that ensures it. It's growing organically in that way because we have like this threshold, like the number of connection is 40. For every node, the number of connection is around 35, more or less. The top is 40. With these numbers, like organically, connections created at random, and the diameter is 2.
Yeah, I mean it's usually there's a formula, right? So it's asymptotically roughly log n divided by k. So we currently only have I think about 200 nodes on mainnet. So yeah, diameter is quite small.
I understand that, but the question is, how do you guarantee that the connections are random?
Well, we cannot guarantee that connections are random for every node since we don't control every node. But at the moment, in a but in a node that is running our code, we sample. When we try to connect to a different node, we sample connections at random. So that's our guarantee, and we are like assuming our implementation is actually using an unbiased sampler.
So basically, you are making an assumption that every node will have a public IP that you can connect to. This is basically the hidden assumption.
I think it is. Like right now, we are assuming that every node has, yeah. And if it is
yes,
not,
that is an assumption.
basically,
Yes.
Yeah.
Mm-hmm. Yeah, we have to have an IP in order to connect to it.
Yeah, but I think Piotr also mean that we not only have an IP to connect to others, but an IP on a port where we are listening to new incoming connections, and we are
exactly.
kind of assuming that. I mean, the code won't break, or we are not assuming that connections are random at all. It just happened that when they are random, the diameter is small, but we are not trying to optimize the topology of the network in any way right now. But that's something that it's also doable. Actually, we are kind of handling managing the topology of the network when, for example, for archival nodes, we try to keep connections between them active at all moments. We don't, if we need to disconnect from one node, we don't try to disconnect from them, but it doesn't try to optimize the topology of the network overall, just some local optimizations. Let's just discuss the rollback cache first, the rollback mechanism first. Like there is this problem that because of the same problem we were discussing before, that maybe the nodes won't keep a full view of the network, and this is something possible either because their routing table is out of sync, or because they actually don't want to maintain the full view because they may think that they are under some type of attack, of this attack. What we have is this mechanism about routing back, that if we send a routing a routed message to some target, and that message requires a response, which is the case for several of our message in the protocol. We have this mechanism that will store in the routing table not only will store in the routing table for every routed message that passed through us the hash of the message itself, which will be used to route back this message. Notice that the most important part of storing the hash of this message, of course, we will store in the hash and the previous hop. So whenever we receive a response for that message, we just route the response through the same path but backward. And with this mechanism, we don't need to. The target of the message doesn't necessarily need to have a route to the source of the message, so they can respond without actually knowing the path to the target. Okay, so this itself might be it's introduce some other attacks. This is, for example, the reason we have before. Let me see if it's open. It's in the announce account. We have in the root message. Rooted message. Sorry, not this. Yeah, in the rooted message we have either peer ID or hash. It is peer ID when it is a forwarding message, and it is a hash when it is a message that is going backward, and it's basically the hash of the message, some identifier of it. And when we are routing the message backward, we just send as target the hash, and this hash is stored on the routing table. But of course, this is another source for leaking memory and for attacking the network. If you just send dummy routed message that requires a response, they will be stored on the routing table, and you can exploit that. So for this scenario, we have this route back cache, which will be basically do it have two types of limit. It has one type of limit, the size, the number of messages it will store at any given moment of time. So this cache will, like, it's just a sized cache, but in order to avoid some type of poisoning that make us remove older messages, what we are doing is that we are allocating some pieces of some sections of the cache to each of our active connections. And whenever like the number of messages stored for each active connection might be more than the allocated section, but if at any given moment in time we need to remove something, we remove it from the peer that has more message allocated in the cache. We also have some other heuristics, such as a timeout, such that message stored in this cache expires, so that we don't keep very old messages in this cache. So basically, with this type of cache, it's kind of last recent cache that it's the less recent element that is removed, but we also have these slots to avoid a malicious peer to dump, like to remove all message from honest nodes. So yeah, right now there is a problem with this type of cache that is being addressed in a PR, but it hasn't been merged, not with the cache itself, but with the mechanism overload. And it's that when we implemented the balancing of the network, that the network has it balances itself so that every peer has from 30 to 35 active connections at any moment in time. The edges are being removed and created. So message being routed back failed to be routed back because maybe some connections no longer exist. So the idea is to enrich these messages, the root back messages, not only with the hash, but actually with the source, with the PID of the source, which in the backward direction is actually the target. And so that if it's not in the cache, we will use regular routing mechanism. And if it is in the cache, we use the path. Okay. So that's something that haven't landed, and it's a problem that it's been addressed. So I think.
I mean, first of all, what do we actually use the cache for? This cache for?
So we use it to store all a mapping from all hashes and PIDs. Sorry if it wasn't clear. So the hash of a message that is being routed, we map it to the PID that sends the message, like the previous hop, the PID from which we receive the message. So let's say node A want to send a message to node D, and in the middle there is node B and C. So when C,
but what is a message like? Is it a block or is it?
No, blocks are not rooted, but some transactions I think are rooted, but I'm not sure if they require responses. But for example, chunk header requests require responses. There are several types of requests which are rooted message because they happen between validators. They require responses, but those nodes don't necessarily need to be connected to each other. So they use this mechanism, and they use the backward mechanism to receive the responses.
So basically, this is like a mapping for all the messages that you are waiting for response, right?
Yeah, basically that. Exactly. So we have this cache. This cache the naive can be abused, and we don't want it to be abused by malicious actors. So we have this cache.
Do you have somewhere written like a list of all messages that?
Yes. Yeah. We have this function which is I think it's called need response. It's not new response.
Expect response.
Expect response. Okay, we have this function. These are the type of the type of rooted message that expects response. Basically, they are all requests. This is just a naive type of message that is used for debugging purposes. I mean, ping. Other are just requests, and of course, each request have its pair, its response, received con request, received con response, etc. So if a message is expecting response, we add root back, which is basically the hash of the message and the peer that was used from when we received the message.
I see, that makes sense. Would need to. Do you have somewhere a document that documents list of all messages and how they behave? Because I would like to.
No, I don't think. Like this list, as I'm seeing right now, this list have grown since the last time I was working on.
Well, I mean, there is a list, right? It's just that
Okay.
I don't think the each type is well documented. What they do exactly.
Probably. Is this the list you mean, Bowen? The list I'm
yes.
seeing?
So
yeah,
this
okay.
is the list, right?
Yeah.
Okay. What's the name of the file? The types network. I see. Chain network source types.rs. Okay, makes sense. Take a look at how we use those.
Sure. So I think that's all I wanted to cover. So if you have any other questions, any other thing you want to discuss, you can do it in the time remaining.
Yeah, I think if there's questions, if anything Marcelo said is not clear, let's discuss it here. But if we're talking about improvements to the protocol, let's not discuss it here because it can go It can take a very long time, and then yeah.
Okay, so thank you for.
Do you have any document that describes how the communication works?
We have this PR that it was started. I can share a link. It was shared in the previous session in the NEP. It's NEP 69. So NEP 69.
Maybe just share a link in the chat or something like that.
Yeah, let me do it. So NEP 69 is just an effort to start describing the network, but it's still work in progress. And actually, I think nobody's working on it right now. I started the work, but I haven't worked on that since a long time.
Okay, so if there's no more questions, let's maybe end it here. And thanks a lot, Marcelo, for walking us through the routing.